I had an idea for how to better conceptualize this. Because this is a lot to take in all at once. So, starting with the most basic idea, the most basic concept of this. The machine that was extended from being a basic state machine to what is called a Turing machine. And so you have linear memory that can be indexed not randomly, but in a sort of iterative progression from one point to another, and then a machine that reads the state at the current head here, and then it changes its own state depending on that, and can also change the state of that datum there. And then, well, technically you could have multiple machines in the same reel. However, they can interfere with each other if they're not synchronized, or if they're not partitioned to specific spaces where they can't interact with each other directly. They can pass information to each other using a specific segment that's been designated for a file in and out. But that's what do you call that? That's going too deep into a tangent. And if if you have the conditions in the state machine programmed correctly, you could have it just read a segment in here as a program and have it execute that program, and that would be a complete machine. And so it would technically be this thing, the control unit here, without the ALU, since, well, the ALU would technically actually be a part of the control unit. It would all be collapsed into one machine specialized for performing one operation. And usually it's binary operations on a single bit in this case, in order to simplify things. And with that in mind, looking at this does have capability for state and iteration through memory, and conditional branching, which is necessary. Haven't programmed the state pathways, however. Trying to think. I appear to have run into a wall now, where it's very difficult to conceptualize what to do next. And there are a lot of daunting tasks, like figuring out how to get this thing to work in the way I'm intending, which I may need to actually not even worry about to begin with. The screen is its own monstrosity right now. Look at this. It can only display one of 4 characters anywhere, and you need to specify whether or not it's going to display any characters, which is another problem entirely. It may be a better idea to take a step back and look at something else for some time. And thinking about replicating a basic one of those simpler machines in order to form the core concept faster. And then perhaps I can just grow that out into what I need later. I'm gonna need some space for this. So it needs an in and an out, a reading and writing, and it needs conditionals, and so that would require something like perhaps just a decoder to begin with. And the final bit will be for the conditional in this case. So it will have a total of 8 possible internal states. There. And the reading point will be this middle one here. I'm going to specify that as well. There. I'm going to remove this because it's redundant. And now the first 8 will be the no, and the next 8 will be the yes in this case. And so it splits at this point. There. Then where I wire these will be the programming phase. That reminds me, internal state holder. Need a register for that. Yes. And then this will be attached to the clock. This final one here is going to be unused. For right now, it may be wise to use a manual clock for most of the time. And then have an automatic one that you trigger on occasion, perhaps. I think this is fine. And attach this to this. And so in the first state, which is like this, the beginning state, where everything is initializing. I feel like I should extend this memory. This is not a lot to work with currently. There. This will be more reasonable. And of course, wire these. At both ends. There. Now it has 12 memory slots, I'm pretty sure. Wait. No, 24. 12 would be 4 times 3. This is 8 times 3, which is 24. And it initializes at this point here. It should begin by, in this case, oh yeah, that reminds me. Actually, it should probably be manually reprogrammable. Or should it? Hmm. I have an idea. Usually, in hardware, there is a mechanism for boot loading, so the machine looks at one of the uh, one of the bootable mediums, usually in an I/O port. These days, you can boot from a thumb drive from a USB slot, and the machine will automatically look for something like that if it doesn't already have something in the boot sector. And then after that, it loads that into the boot sector and begins to run it. However, right now we have no bootable medium, and so everything we do would need to be programmed in hardware, which is the least ideal way of doing it, the most inflexible possible. I should try to make a simple hardware program to prove that this does in fact function as a simple machine. What about the first state? It writes a 1 and then moves to the right, and then in the next state it writes a 0 and moves to the right, or doesn't write anything since it initializes to 0. Ah, until it hits a 0 and then it does something else. If I have this wrap around, then it should be able to eventually interface with its own work, which will allow it to perform more complex tasks with less program. There, now it's recirculating. And so in the first state, oh, of course. You see, this can't be a decoder, it needs to be a splitter, because it needs to be synchronized to the clock yet again in order to function correctly and not destroy everything. Fortunately, removing this is simple, because I did this correctly. The board is modular, yet again. And now I just quite simply attach this back to where it's supposed to be. There. And now this will activate on every clock cycle as well. I really want to change the color scheme of this clock though. It's bothering me. We had a designated scheme the entire time beforehand, so why not still? As I'm sure you're aware, I like to keep this, the color tool, kept at black when I'm not using any specific color. It's just a way my OCD presents itself. Now then. I'm going to get rid of that now. Wait. Never mind, hold on. What I really wanted to do was delete what was on the list, not what was in blueprint memory. Now, oh yeah, hold on. I need to do that with this as well, since this is its precursor. Now I can finally begin work on this program. A very simple program. So, in state 1, it both switches to state 2 and flips the bit that it's working on. then in state 2, I just noticed something. In order to move through memory, we're going to need to activate all of these pins, all of them. And I want actually to do this the lazy way. And also revise this entire design, since it's not conforming to the new standards, which is bad. It's always bad to have not predictable standards. Yeah, step 1, and now step 2. I just need to remember which way these go. Yes, it's very important that I get these the right way around. And now I just wire them correctly. And this will make everything much simpler by adding one small abstraction layer that only causes one tick of delay. What would be a better name for that, because that's kind of a stupid name, isn't it? Yeah, one cycle of delay. A 1 unit delay would be a more standard way of saying it. The simplest way to say it would be a delay of 1, since time is implicit in this case. I think that would be the best way to do it. What's the name of this object? And now I can revise this as well. And everything becomes so much simpler. Instead of 48 inputs I need to wire, it's down to 6. And just getting rid of all of these redundant boards, since some of it will need to hang off of the end anyway. There. And now with the second step, it will move to the right. No, that would be to the left. To the right in memory. Oh, here's another thing I forgot. So this will be one small repair. Which is actually going to be easy because I actually memorized exactly how this machine works. And then this one to here. And it's finished. And so now, on the second operation, it's going to move to the right in memory by moving the entire memory to the left relative to itself. And then it's also going to move to the next step, which is going to be to go to step 3 in the plan. In the third state, it will do nothing except move to the left again. And then after it moves to the left, no, to the right, it will revert back to stage 1, in which case it will write another one to memory. I'm interested to see if this works. What is this? Oh. Hold on. Something I need to fix really quickly. Not expecting this to be a problem. Now, do you mind trying to do something here? Having mysterious problems. Now, this should fix the problem. Something I didn't account for. The color is irritating me, so I'm going to fix that also. And now it should run correctly again, or for the first time. Oh, timing, of course. And, well, there's a lot of things I forgot about, actually. Oh yes, and so, since it will be sitting on a 1 that time, it will actually change to state, what would that be, 2 plus 8? So the 10th state. This one, I'm pretty sure. Oh, and this got uncolored. So hold on. This one and this one. And so that would be like that. This one. You see how many things there are to account for in such a complicated system. Yes, and then after that, it should just be a mimicry of this one. And then at that point it will not be on a 1 anymore, so it can just do the operation unconditionally again. Oh yeah, that's another thing. It needs to be an unconditional set, so that we don't need to account for this every time. There should be unconditional instructions and conditional instructions. Actually, I think it would be best to have only one instruction that is fully conditional, the jump instruction. Yeah, that's the only one that makes sense to me. And now, trying to predict if this will work, finally. Oh, I forgot the last problem this has. So the final problem is this timing here, which actually comes from another problem. it does need a decoder. There. And so now this will be on without the clock. And so this way, you go to here, and you go to here, and then the final one doesn't go anywhere, and that would be this one. This is the final one. Which means you should also deconnect, since you'll no longer be doing anything. Oh, this is mysterious. Oh, that's why. Oh, here's another problem I forgot about. So, it's in state 1 here. A fail state. Now try. Yes, now it's executing correctly. It is printing a 1 to memory and then moving 2 spaces to the right. And so this is successfully hardware programmed with a ROM. A hand-wired ROM, not even an EEPROM. And now it should enter the fail state because it encountered a 1, and because this is a conditional instruction, it breaks because there's no instructions for if it encounters a 1 in this case. So there's actually problems with this that I didn't think about. I should have been aware of, but I wasn't. I think 8 units is an appropriate speed now for testing quickly. I think it could be even faster. 4 units. Oh, look at the speed. Yeah, this is beginning to feel much more powerful now. Now I just need to refine this design and make it more practical, and then I can grow it into being more like that. I feel that would be a better idea than what we were doing before. I start small instead of starting massive. So, there should be conditional instructions and unconditional instructions. Trying to think of exactly how to implement that. And I'm also going to want to fix this problem so it never happens again. There. Does this one have the problem? I'm about to find out. Yes. Yeah, that's 2 problems fixed. So that's going to be prevented in the future. Hmm. Now, this is working very well so far. I just need to refine it somehow. Hmm. How am I going to have this separation happen? Hmm. So far we technically only have, what, 3 things we can do? We can shift memory left and right, and we can flip bits. And these things can all happen conditionally. In fact, they can only happen conditionally in this current configuration. What if I have a conditional rail and an unconditional rail? So that way there would need to be 3 of these here. And so there'd be 1 for conditional, 1 for unconditional, and 1 for preload. Preloading the next state for purpose of well, it's obvious. And then these can all be stacked on top of each other. Or horizontally. I think horizontally would be preferable in this case. Yeah, we're going to need a clock, as always. One of the vital components of any of these machines. Where did I put the clock? Here it is. And going to need state. So that this is obligatory. That gives me another idea. We're actually not using all of this state currently. Using some of it for conditional. Requires thought. This, I would like to be on a platform first. There. Back here I can put the state. And I can put the clock right here. And the clock can then route to the state, as well as the executions. Preload doesn't need clock. And so, in this case, we're also going to have conditional and unconditional. This will be the unconditional. And I'm actually going to harvest this component from this inferior design. and then I can put that back into this machine. At this point, I might as well. And that can route like this. There. And so this is the working end again. Going to reset everything. And at this point, I'm going to need to wire this to here for conditionals and wire this to here for unconditionals. And so now you can see this time when that bit is off, it only fires this rung of the kind of logic ladder, and then when it's off, it only fires this one. And so now there's 32 possible instructions from a machine that has 16 possible internal states, but one extra possible external state that it can import, and so that brings it up to 15 possible working state bits. 15? No, 5. And so now you see when it's off it turns on, and when it's on it turns off, which is exactly what we intended to happen. And I'm going to fix this again also, because this is broken again. Oh yes, and now these can wire to here. Which will then complete that part of the design. And then this is the rung that wires back into the state. And these are the rungs that control the shifting left and right and flipping of data. This all looks correct. Technically, the correct way to do this is to have a 5-bit decoder, and so that way the fifth input is this here. Technically it is a 5-bit decoder actually. It just has a lot of redundant parts and is decentralized. With enough possible internal states, you should be able to finally have this emulate a regular processor in some way, although for that you would probably need a lot of space in memory to store the software for the emulation to occur with. There should be at least one in hardware instruction, I think, to move in either one of these two directions until it reads a specific number or a set of bits in order, at which point it switches state to doing something normal again, so that it can seek to spots in memory by index. For doing work with numbers instead of solely logic, I feel it's ideal to have a lot more internal memory in here for things like counters. A counter would be very useful for keeping track of where you are in memory. without needing to read memory itself to figure it out. Hmm. Yes, and this is the counter built in, and so that's all correct. Now this here actually also looks, I think, correct. Yes, this is actually a mimicry of that design. I should bring that closer so I can compare it more easily. In fact, I would like to save this now. And with the clock, that's correct. And here we have these. Yes, another component we're going to need. Yeah, which would be, I think, here. Now that would be the decoder for purpose of uh, of wait. We can't conditionally change our internal state. That's a problem. That would mean we don't actually want to change our external state conditionally, only the internal state for jump instructions. So in reality, oh, I see now. So we're going to want to have internal state change depending on external state, not the other way around. Somehow I had it backwards in my mind. And now, this design is looking progressively more outdated. The idea was correct, I'm pretty sure, as far as I'm aware, but the implementation was wrong. This design, I'm pretty sure, is still pretty good, except for this part, the flag. Still need to figure out the flags for conditions. I like the idea of the comparison flag operator for comparing two numbers in the stack. But now I'm beginning to realize also I'm going to need a way of deciphering relative, which one is bigger than the other, which is another more complicated problem. Could potentially have that parallel processed, and so that way you would have an adder subtractor specifically for determining a comparison of two numbers. Trying to think about this critically. Hmm. I may need to completely revise whole entire sections of this idea, which is not uncommon actually. That's fine to do. The worst thing you could do is keep trying to make a bad idea work and failing in the same way every time. That's unproductive. Hmm. I feel like I'm going to redesign this module here. That module should be fine. This module just needs some other modules attached to it to start functioning correctly. Uh, Actually, this also needs a few modifications in order to have the conditionals work, but the conditionals are the only part of this that doesn't work right now. Or at least that I'm aware of. Actually, we're going to need importing and exporting between this and the main bus. I'm not entirely sure yet how that's going to work. Hmm. I'm pretty sure it can't run at such a fast clock speed to begin with. Hmm. Hmm. Walking around silently thinking about something. I'm just now realizing that's probably not great. Uh, but it's so difficult to try to think of what exactly to do next after all of this. Actually, I know exactly what to do. I should end the video because it's been almost an hour now.